Assalamu alaikum wa rahmatullahi wa barakatuhu, and good morning to everyone. Today I am going to teach you the second session of the we left last day. Earlier we studied about what is an elementary reaction and molecularity of reactions and the reaction mechanisms related to that ozone gas is converted into oxygen and some CFC chlorofluorocarbon and how it gives that chlorine free radical and how it reacts with this ozone gas to convert it into oxygen gas. Right, I hope you have went through the videos, and today we'll discuss about the rate laws of elementary reactions. Right, we know that rate means change divided by time, right? Rate of change of concentration or rate of change of maybe rate of change of concentration or rate of change of mole amount. For example, if an hypothetical reaction that A converted into P, if this is in the elementary reaction, if they have told you this is an elementary reaction, then how you can, for elementary reactions, we can write rate law. How you will write the rate law, because this is an elementary reaction, no? The same mole amount of that reactant will come as the rate order of that relevant species concentration. So that this is A converted into P. If they tell you that this is the elementary reaction, then we can express the rate law as rate equals rate of the rate constant into concentration term of A, and 1 to the power concentration term of that A. That means this is elementary reaction, so that stoichiometric number of this A is 1, so that R equals K into A's first order, right? Because this is an elementary reaction, right? And for elementary reactions, we can write rate laws like that. And the same amount of that stoichiometric mole will come as the rate order. So, and another example, we can see an elementary bimolecular reaction has a second order. If they are telling you that elementary bimolecular reaction is 2A is converted into P. This is an elementary reaction because they are saying that with the practical evidence, right? So that this is an elementary reaction, so that this is the RDS step. So maybe RDS step, so that R equals K into concentration of A second order, A to the power 2, because stoichiometric number of this reaction is 2 and this is the elementary reaction, right? And another example we can go through, that is that another reaction A plus B are the reactants, they will react to give you the product P. Then if this is an elementary reaction, how you can write the rate law? R equals K into A to the power 1 and B to the power 1, right? The overall order is 1 plus 1, 2, right? So that this is a bimolecular elementary reaction, right? Because here see, they have told you that a bimolecular elementary reaction is second order because its rate is proportional to the rate at which the reactant species meet, right? Which in turn is proportional to their concentration. Therefore, if we consider that a reaction is a single step bimolecular process, we can write the rate law, right? But they will say it is an elementary reaction, right? And now then you will have understood that molecularity, and if this is then molecularity they have given because this is an elementary step. If for example A turn into P, R equals K into A to the power 1, because this is an elementary reaction, then molecularity is 1, so that A to the power 1. And if the bimolecular reactions, because two molecules collide with each other to give the product, so that R equals K into A to the power 2. Two molecules are colliding to give you the product, so that rate law becomes like this one. So then this is elementary reaction, so the rate law is like this, so that this is an molecularity is also 2. And another example they have given you that A plus B reacts to give a product, so that rate we can say as K into A to the power 1 and B to the power 1, because this is the elementary step. Likewise, you can go through term molecular reactions and unimolecular and bimolecular reaction. You can go through the chart. Right, I hope you have understood how to write the rate law if they give you the elementary step, right? And again, in a reaction mechanism, that means multiple step reactions, right? For example, we will say if A gas turn into P gas, right? Then, but this is not a single step reaction. This is not a single step reaction. Then first step is, then this is the overall reaction, right? But first step happens like this one. First steps, step one. A is converted to B, right? Then rate constant for that one is K1, right? Then step 2, then now B is the intermediate. B is the intermediate that converted into P. The rate constant for this step is K2, right? This is a net reaction, but it happens in a two-stage. This is a two-step reaction. Then in the first step, it converted into B, that is an intermediate. We did not add that one earlier, but it came in the middle of the reaction. So that's an intermediate. Again, it's really unstable. Then what will happen is B is converted into P. Right? Then if the two stages or steps are like this one, any one of these the reaction step may be that faster step, and it may include a slower step, right? According to K1 and K2, if they have given you the data, K2 is much greater than K1. Rate constant for step 2 is much greater than K1. That means K2 is great, so that rate is very high relative to this K1. So that this is the K2, K2 that includes in step 2, that is the fastest step, right? That is the faster, the step 2, this is the faster step, fast, right? Second step. Then this is the slower step, slower. Then which step will be the RDS, rate determining step? You can conclude that is the step 1 because that is the slower step. Faster steps will quickly, that will end up, but we have to wait until the slower step to complete. Otherwise, the reaction won't be completed. So that this slower step of the reaction is the rate determining step. That means RDS. Right? Then in the according to RDS, this is the RDS. No? Second first step is the RDS. Then how can write the overall rate law? How we can write R equals K to the power K into, in the slower step, 1A is there, A is present, A to the power, only in slower step, 1A is there, that A1. You can, we'll write like this one as R1 is equal to K1. K2, no, they have given, oh yes, K1 into A to the power 1. Right? This is the slower steps, that rate law expression. This will resemble the net reactions R. That will be same like net reactions R equals K into A to the power 1, because this is the RDS. That will resemble net reactions rate law expression. For this step also, we can just like this one, right? For second step, R2 is equal to K2 into only 1B in the equation, stoichiometric number is 1, so the B to the power 1. But this is the fastest step, no? Fastest step. Then first one. So that this won't this is a multiple step reaction. All the steps are elementary steps. For the elementary steps, we can write the rate law, although we can write the rate law like this one for R2. Because why? This is an elementary step, no? For this one also, we can write like this one. But overall reactions are rate low. Overall reactions are rate low. Overall reactions rate low. Overall reactions rate low will be like the resemble that will resemble that RDS steps rate low. Right? Because then K2 is much higher than K1. K2 is much higher than K1. K2 is the fastest step. Then slower step is first one. Then first one is the element, the first one is an elementary reaction, so that its rate law will resemble overall reactions rate law. Okay. You have to plot you have to find out the rate law expressions by reading the data very carefully, right? For that, another example we can go through, that is NO2 gas react with carbon monoxide. NO2 reacts with carbon monoxide to give nitrogen oxide plus carbon dioxide. This is the net reaction, right? Then, but this is, although this is an reaction, but it happens in two steps, right? It has a reaction mechanism. In the first step, what will happen? In one NO2 gas with another NO2 gas with another NO2 gas, right? NO2 gas with another NO2 gas, it will react to give one NO3 plus NO. NO3 plus the remaining one is NO. That is the first step. But, right? And they are telling you that this is a slower step than second one. Then it's a slower step, means that's a RDS. Right? Again, this NO3 is an intermediate here. It is not in the product, so that NO3 intermediate and with another CO reactant, it's reacting to give one NO2 gas and CO2 gas. Right? This is the fastest step. Then NO3 is in both sides, so that we can cut off that one, and this NO2 also two sides, it can cut off that one, so that overall reaction, net reaction will come like this one. First one, right? This is the reaction, but that happens in, this is the main reaction, right? Main reaction is NO2 gas plus CO gas reacts, and they are giving you NO gas plus CO2 gas. This is a net reaction, right? Net reaction. This is the net reaction. But it happens in two steps. In the first step is a slower step, one NO2 from this one NO2 from the come here, and it's reacting with another NO2 gas to be NO3 gas. This is the intermediate, and one product is coming from here, right? Then NO3 means as intermediate, that will go to second step intermediate. Again, it will unstable, so that will react intermediate, and another CO molecule is there to react. It's giving you one NO2 and another product here. Then this were two sides, one NO2 is coming, we can cut this one, right? And NO3 also will go, and overall that reaction you can find out NO2 plus CO, one NO plus CO2, right? And first one is the slowest step. Then what you can say about that rate constants K1 and K2? Then K2 is greater than K1. Right? We can say here K2 is greater than K1, much greater. So that's the fast step. Second one is the fast step. First one is the slowest step. Right? Then, according to the, which one is the RDS now? The first one is the RDS. First one is the RDS. So that, how will you write the overall reactions rate law? With the slower step, you can write down rate equals K into two NO2 molecules are participating in RDS, so that NO2 second order with respect to NO2 gas, right? But that is zero order with respect to CO gas. Because why? Then in the slower step, only two NO2 molecules are participating, not any carbon monoxide gases are participating. So that in the rate low, only NO2 gas to NO2 gas will come. So that rate low you can find out as a rate equals K into NO2 second order, right? Second order with respect to NO2 gas, right? Then NO3 is the intermediate of the reaction. But as these two steps are that elementary steps, this is a mechanism of both are elementary steps. So that we can just write like first one R1 is equal to K1 into NO to the power 2, right? Because this is the elementary step. For second step also, we can just write R2 is equal to K2, 1 NO3 in R2 in the second step, 1 NO3 gas and 1 CO gas are participating. So that one NO3 gas, one CO gas. R2 is equal to K2 into NO3 plus into CO gas. Likewise, we can express the expression like this one, but that overall net reactions rate low R will resemble the first one because that is the rate determining step. Right? Then we can say that one conclusions they have given you, you can read here. If K1 is K1 is resembling the overall net reactions K, right? That is becomes identical to the observed rate law, right? Observed rate law is according to the practical data. That is identical to the first step, right? Because the first step is the slow one, right? That one they have given you. CO does not appear in rate law. That means what? Reaction order of the with respect to CO gas is zero, right? Because it takes part in the mechanisms after the rated RDS. Because this is also an important the thing they have told you, because it takes part, the CO takes part in the reaction mechanism after the rate determining step. After the rate RDS finishes, only CO is coming to the action, so that the rate order with respect to CO gas is zero. CO gas is zero. Right? Likewise, we can write down. Right? Did you understood? Then how you have to right? How you have to plot the overall reactions rate law using RDS, but all the steps are elementary steps. You can write the rate laws, but overall reactions rate law will resemble the RDS step, and the species participating in the RDS, right? And likewise, you can go through another example also. NO2 plus F2 gas, 2 NO2 gas plus F2 gas give you NO2F, right? Then experimental rate law is the first order, that is first order in NO2 and in F2, right? Then experimental rate law gives you the data R equals K into NO2 plus F2. Then in the RDS, one NO2 and one F2 is participating. Then we can write the RDS now, because they have given you net reactions rate law they have given, right? In the net reactions rate law, one NO2 and one F gas is present. So that in the RDS, one NO2 and one F2 gas is in the exchange. Right, then we can write NO2 plus, then first step how you can write down. The NO2 plus, according to this one we are writing. Right, one NO2 plus F1 NO2 plus F2, then will give you the one product it can give. Right, this is the net reaction now. This is the net reaction. Then using one NO2 and F2, we cannot write down two NO2F. Only one NO2F only we can write. So that I am putting writing one NO2F here. Right? And then that if I write like this, one F gas will remain. That is the intermediate. Then what will happen? It will go into the exchange for the second step. Right? And then F2 gas has come here. F1 F gas, that is the intermediate, has come here. Then net reaction, overall reaction is this one. In the overall reaction, the first step has finished, but one NO2 gas is remaining. I did not react till now, so that remaining NO2 have come to the step 2. Right? Then one NO2, then intermediate also came. Now using this one, NO1, NO2F, we can write down. Right? First we wrote one product from the net reaction. One product we wrote from the net reaction. Now one product I am writing in for the faster step. Right? Likewise, you have to plot the mechanism if they give the rate law. Can you? Right? This is the net reaction, but they have given you with a rate law expression what is the RDS they are saying passively, right? Then one, the RDS is like this one, that is the rate determining step. One NO2 gas plus F2 gas will react to give NO2F. Right? Only one NO2F we can write. With one NO2 and one F2. Two NO2Fs we can't write now. Then one NO2F I am writing means one F gas is remaining. That is the intermediate. That will come into the exchange for the second step. Then in the second step, what is them? Another reactant. Then net reactions, one NO2 came in the first step, and another NO2 is remaining. That come to react with the intermediate. Right? The remaining NO2 came to react with this one. Right? Then NO2 plus F. Now one NO2F, another NO2F from the product will come here. That is the faster step. Right? By using likewise, you should plot the mechanism if they are giving the net reaction and the rate law. Earlier we discussed how to write the rate law using the RDS and net reaction, using net reaction and RDS and K1, K2 data. How to you have to find out the net reactions rate law expression. That is a question for first one, right? And for the second question, right? The second question, and NO2 and F2, they are giving the net reaction. They are giving the net reaction, and they rate law they have given you. Using that, you are writing mechanism, right? And another reaction or example also there. You can also go through that one and right. you can find out what I am saying, explaining here. Right? That is the thing they have given you. Then we can say like this one. Another one is if the another reaction is A is consecutive elementary reactions, right? Reactions which goes through an intermediate can be expressed as A is converted to I is converted to P, right? Then, if the first for the elementary step, you can write as R equals that, and that is the concentration of A is decreasing, so that they have given you like this one. R is equal to K1 into A to the power 1. That is a unimolecular reaction. For the second step, right? For the second step, you can write down R2 is equal to K2 into the reactant of for the second step is intermediate I, right? So that you can K2 into I. Likewise, you can write down. Then you can say concentration of A is decreasing with time, and concentration of the intermediate I, and that is initially it is formed, so that concentration of that one is rising in the first step, and that falls to zero within a short time interval, because that is an intermediate, right? First step and then intermediate is formed, right? This is the graph describes with the concentrations of the A means that is the product, and that is the reactant. The reactant is like this one. A, yes, first it turned into I, and after that I is giving the product. Right? This is the intermediate. Then this is the reactant. A is the reactant. This is a product. Reactant means the concentration of that one is earlier. If you see the graph, green color graph, green color graph, right? That reactant's concentration is initially higher, that is decreasing with time. If this is an one side reaction, this is not the that reversible reaction, so that it becomes reaches zero, while the when the all the A molecules are consumed, so that first initially that A's concentration is very high, and after that that is decreasing with time. And what will happen is we have to now consider about the concentrations of intermediate, right? Intermediate we did not add. Then initially that intermediate concentration is zero, but it is increasing with time. It quickly increase, because if quickly increase means that first step is faster. So that quickly it has increased. Then after that, with time slower step, if the first step is faster step, we will say the first step is so that, right? first step is fastest step, so that second to my cursor. Right? Then product's concentration is initially 0, and after some time, product's concentration is increasing. Right? Then, so that you can find out the graph like this one. And sometimes the first step may be that slower step. And if the step is slower means slowly that will happen, so that little bit of that intermediate is formed in the first step. You see, 3 types of graphs they have explained you. Right? In the graph A, right? In the graph A, you see, then we explained this graph like earlier. The first step is fast means intermediate concentration is quickly rising, and after some time, if the second step is slower step, so that concentration of intermediate is decreasing slowly. The slope of that one is first one is higher. But it has reached a maximum concentration because in the fast step it's formed. Sometimes the first step, if the first step is lower, then what will happen? Little bit of that S concentrations will, that reactants concentration will, however, that will decrease, and products concentration will increase with the time. But that intermediate concentration slowly increase, and after that it will disappear in the second step, because the first step is lower than the second step. That is, the graph becomes like this one. And if the first step is very much slower, that means second step very much faster than first step, the little bit of that, because second step very fast, first step is very slow compared to second step. Then little minute amount of intermediate concentration will come, that very hard to detect that concentration also, that will also disappear after some time, because the second step is much faster than first step. Right? And then with the relevant intermediate concentration for different 3 types of reaction mechanisms they have given you. But that ACE concentration, that means reactants concentration and products concentration, will change like same for all three graphs. But if the reaction first step of the reaction mechanism is very speed, and second one is the RDS, then what will happen in the fastest step only, then a very much higher concentration of intermediate can be seen, so that intermediate concentration is quickly, it will rise, and after some while it will decrease. And for the second graph, you can go through, then intermediate concentration is increasing, but that is very lower with comparison with the graph A, and after that will also decrease in the second step. If the first step is very much slower comparing to the second step, then the second step is very fast, so that first one is very slow. Little bit of this minute amount of this intermediate concentration will come, and that also will disappear after some time. This is the rate, that graphs with relevant concentrations with time we have plotted, right? You can uh, just plot and check and study, right? Again, and in the next class, we will discuss about the pre-equilibrium that exists in a mechanism. Then how you have there is an equilibrium situation comes in a multiple step reaction, how to write the rate laws and how to that replace the intermediates and everything we are going to discuss in the next class, right? Because you can't get everything in one session, so that I will upload that in the next video. Then what did we study today? Then we went through the reaction mechanism and different type of element reactions when they are giving, and how to write the rate laws, and using the we have to identify the RDS, and that RDS will resemble the rate law of the overall net reactions rate law. And if they are giving you the that elementary step and slower and fast step, you can find out the rate laws, right? Likewise, reversely, if they are giving you the rate law, and if they are giving you the rate law, you also have to write down the mechanisms that also we studied with relevant to this NO2 gas reaction. We studied that one. You can just go through. And after that, we discussed about, right, how the intermediate concentration changes with time, and for if the first step is faster than second step, how you have to plot the graph, and if the second step is faster than first step, then how you have to plot the graph we discussed. Please study and go through the notes very well before I am uploading the next video, right? And Assalamu alaikum wa rahmatullahi wa barakatuhu, and good day to you all.